Now we're going to talk about computer systems and how energy and power come into play with them. So what we're going to cover today is we're going to start off with just the difference between energy and power. And this is pretty straightforward. You probably saw it in your first physics class, but we're going to review it again just to make sure we're clear about what we're talking about. We're then going to go into how computers use energy. So where does energy get burned when you have a processor these days? And we're going to talk about why this is a problem. And here you're going to run into something you may not have seen before, and that's a concept called Dennard scaling. So you've probably heard of Moore's law, but you may not have heard of Dennard scaling, and you're going to see why it's a real problem that this has come to an end. Then we're going to talk about where computers consume energy. So if you look inside a computer, where is the energy actually going? And finally, what we can do about it. So the goal here is for you to understand where the energy is really being used in the machine, why it's a problem now, what's going on inside, and what we're doing about it, to put this all together to understand the energy picture. So before we get going, let's go through a few questions here. So what is the difference between energy and power? Well, energy is an amount and power is a rate. So energy is just the number of joules and power is the joules per second or watts. So the total amount of energy used, just the sum of all the power used. And what this is, the thing that's important to remember here is that power tells us how much energy is used at a given time. The maximum power is limited by how quickly you can cool it. So to see an example of this, energy, we could say a double precision operation, so that's a double precision multiplication, takes 20 picojoules of energy. Okay. If we look at power, you can say a GPU that does 3 billion operations per second, so this is a rate, consumes 225 watts. So when we say energy, we're talking about the energy to do, the amount required to do a particular thing. We're talking about power, we're talking about the rate of consuming that energy. Here's a question that's related to that. So what does a larger battery give you? Well, a larger battery basically just allows you to store more energy. So if you store more energy, then you can use more energy, so you can get a longer battery life, or you can run for more time at the same power. So if you're using 4 watts and you have a battery that's twice as big, you can run for twice as many seconds because you got twice as many joules. However, the size of the battery doesn't allow you to use more power. So if you want to pull more power out of a battery, you need a battery that's designed for that. A larger battery may just catch on fire if you pull out twice as much, even though you could pull out the same amount for twice as long. When we talk about performance, though, batteries don't really give you performance. Performance is a function of power. That is how many joules you can pull out per second. If you can pull out more energy, you can do more computations, you can get more power. But a larger battery doesn't necessarily mean you can pull out more power. All right, how about heating and cooling? So what determines how much cooling you need in a computer? Well, the amount of cooling needed is a function of what the power is, so how much power are you putting into the computer using, and the maximum temperature for the transistors. So obviously if the transistors get too hot, they stop working. And it's actually somewhat worse than that. When transistors get hot, they start leaking more energy, so they start using more energy, so they get hotter and hotter, and you can get this thermal runaway, where things just get hotter and hotter. The power that's going in the system tells you how much energy you're using, and if you're putting energy into a system, it's got to go somewhere and it comes out as heat, so that tells you how much cooling you need. Now you might think that the thermal mass here plays a role, but the thermal mass is just with transient power. So your average power is what you have to cool. So if I have a laptop that's using 20 watts of power, it's going to heat up really quickly, but I still got to cool 20 watts. If I have a desktop that's using 20 watts of power, I've still got to cool 20 watts, even though it's going to take a lot longer before it gets hot. On average, you still have to cool off what the average power is.